Linked lists. In this chapter, you will learn about linked lists, become aware of the basic properties of linked lists, explore the insertion and deletion operations on linked lists, discover how to build and manipulate a linked list, and learn how to construct a doubly linked list. Learn about linked lists with header and trailer nodes and become aware of circular linked lists. You have already seen how data can be organized and processed sequentially using an array called a sequential list. You have performed several operations on sequential lists such as sorting, inserting, deleting, and searching. You also found that if data is not sorted, then searching for an item in the list can be very time consuming, especially with large lists. Once the data is sorted, you can use another search algorithm called the binary search, which we will cover in the next weeks, and improve the search algorithm. However, if the list is sorted, insertion and deletion become time consuming, especially with large lists, because these operations require data movement since the resulting list must also be sorted. Moreover, because the array size must be fixed during execution, new items can be added only if there is room. Thus, there are limitations when you organize data in an array. In this session, will help. This session helps you to overcome some of these problems. In the previous lesson showed how memory can be dynamically allocated and deallocated using reference variables. So this session uses reference variables to organize and process data in lists, and these are called linked lists. Recall that when data is stored in an array, memory for the components of the array is contiguous. That is, blocks are allocated one after the other. And on the other hand, as you will see, the dynamically allocated components of a linked list are not necessarily contiguous. A linked list is a collection of components called nodes. Every node except the last node contains the address of the next node. Thus, every node in a linked list has two fields, one to store the relevant information, for example the data, and one to store the address, called the link, of the next node in the list. The address of the first node in the list is stored in a separate location called the head or first. The first figure is a pictorial representation of a node. It has data and link, or the address of the next node. In Java, there are two types of variables of the primitive data type and reference variables. Therefore, in this figure, the info or the data of the node can be either a value of primitive type or a reference to an object. A linked list is a list of items called nodes, in which the order of the nodes is determined by the address called the link, stored in each node. In the second figure, shows an example of a linked list. The down arrow in the last node indicates that this link field is null. The arrow in each node indicates that the address of the node to which it is pointing is stored in that node. For a better understanding of this notation, suppose that the first node is at memory location 1200 and the second node is at memory location 1575. We have this figure. The value of the head is 1200. The data part of the first node is 45 and the link of the first node is 1575, which is the address of the second node. The second node has an address of 1575, its data is 65, and the link is null. We assume that the data type of the variable data is integers in this examples. However, as remarked previously, the data can be either a variable of a primitive data type or a reference variable. In fact, after describing in the next few sections the basic properties of linked list and how to build a linked list, we'll develop a generic code to process linked lists that can be used in a variety of applications. Moreover, for simplicity and ease of understanding and clarity, our previous diagram use integers as the values of memory address. However, in computer memory, the memory addresses are in binary. Because each node of a linked list has two fields, we need to create a class, say linked list node. The data type of each node depends on the specific application. That is, what kind of data is being processed. However, the link field of each node is a reference variable. In fact, link is a reference variable of the linked list node type. For the previous linked list, the definition of the node is as follows. Suppose that data or info is of the type int. So we have this illustration or the declaration of a node using a class, public class linked list node, and the data in our node is stored in public int info, and the link of the node is public linked list node link. Notice that the class linked list node to implement the nodes of a linked list is declared as public. Moreover, notice that instance variables of the class linked list node are declared as public. The instance variables are declared as public for the simple reason that in the next few sections, our focus is on the basic properties such as traversing a linked list, item insertion, and item deletion of a linked list. To directly access these instance variables, we have declared them public. If we declare them private or protected, then we have to provide methods such as set and get to manipulate the data stored in the node. However, when we study linked lists as abstract data types, we will declare the class linked list node as protected. We will also make it an inner class of the class that implements linked list as an ADT so that the user does not have direct access to the instance variables of the class linked list node. Furthermore, as we marked earlier, for illustration purposes, the data type of the instance variable info is int. The following statement declares head to be a reference variable of the linked list node type. To help you better understand the concept of a linked list and a node, some important properties of linked lists are described next. Consider this figure in figure 4-4. This linked list has 4 nodes. The address of the first node is stored in head, that is 2000. Each node has 2 fields, info to store the info or data, and link to store the address of the next node. As you can see, the first node has an address of 2000, the second node has 2800, the third node is at address 1500, and the fourth node is at address 3600, and the head is pointing to the address 2000. And each link of the nodes points to has the address of the next node. Suppose that the first node is at location 2000, the second node is at location 2800, the third node is at location 1500, and the fourth node is at location 3600. Therefore, the value of head is 2000 because the head must point to the first node, and the address of the first node is 2000. The value of the link field of the first node is 2800. That is the address of the next node or the second node. The value of the link field of the second node is 1500, and so on. Also, null in the link field of the last node means that the link field of this node does not point to anything, which we indicate by drawing a down arrow. The number at the top of each node is the address of the node. Table 4-1 shows the values of head and some of the nodes of the linked list in figure 4-4. We have the head. Its value is 2000. If we have head.info, the value is 17. Because head is 2000 and the info of the node at location 2000 is 17. Next, head.link. The value is 2800. Because head points to the first node and the link of the first node is 2800. Next, head.link.info, that is 92, because head.link is 2800 and the info of the node at location 2800 is 92. Suppose that current is a reference variable of the same type as head. Then the statement current equals head copies the value of head into current. See figure 4-5. Figure 4-5 is a linked list after the statement current equals head executes. Because of the current equals head, current copies the value of head, which is 2000, and they both points to the address 2000. Table 4-2 shows the values of current and some of the nodes of the linked list in figure 4-5. We have current, its value is 2000. Current.info, its value is 17. Because current is 2000 and the info of the node at location 2000 is 17. Current.link is 2800. because current is 2000 and the link of the node at location 2000 is 2800. Current.link.info is 92 because current.link is 2800 and the info of the node at location 2800 is 92. Now consider the statement current equals current.link. This statement copies the value of current.link, which is 2800, into current. Therefore, after the statement executes, current points to the second node in the list. When working with linked lists, such as when we traverse a linked list, we typically use these types of statements to advance a reference variable to point to the next node in the list. See this figure. This is a linked list after the statement current equals current.link. And the table shows the values of current and some of the nodes of the linked list after advancing current to the next node. Current now is 2800. Current.info is 92. Current.link is 1500 and current.link.info is 63. Finally, in this table, we show the value of some other reference variables and nodes of the linked list in this figure. Head.link.link is 1500. Head.link.link.info is 63. Head.link.link.link is 3600. Head.link.link.info is 45. Current.link.link is 3600. Current.link.link.info is 45. Current.link.link.link is null. Current.link.link.link.info does not exist. From now on, when we draw the figure of a linked list, we use only the arrow notation. Some properties of linked list are the following. The address of the first node in a linked list is stored in the reference variable head. Each node has two components, one to store the info or the data, and one to store the address of the next node. Head should always point to the first node. The basic operations of a linked list are search the list to determine whether a particular item is in the list, insert an item in the list, delete an item from the list. These operations require the list to be traversed. That is, we must step through the nodes of the list. Suppose that head points to the first node in the list and the link of the last node is null. We cannot use the variable head to traverse the list because if we use head to traverse the list, we would lose the nodes of the list. This problem occurs because the links go in only one direction. The reference variable head contains the address of the first node. The first node contains the address of the second node. The second node contains the address of the third node, and so on. If we move head to the second node, the first node is lost unless we save the address of this node. If we keep advancing head to the next node, we will lose all the nodes of the list unless we save the address of each node before advancing head, which is impractical because it would require additional computer time and memory space to maintain the list. Therefore, we always want head to point to the first node. It now follows that we must traverse the list using another reference variable of the same type as head. Suppose that current is a reference variable of the same type as head. we can use this, we can give an example code to traverse the list. This is our code to traverse the list. For example, we have current equals head. So this copies the head. So we won't be moving our head, and this means that head will always point to the first node. Then we have a loop while current is not equals to null, because our current will have to move from the first move up to the from the first node up to the last node. So we have while current is not equals to null, then current equals current.link. This will move the current node to all of the nodes, to all the nodes. For example, suppose that head points to a linked list of numbers. The following code outputs the data stored in each node. Current equals head, while current is not equal to null, system.out.println current.info plus space. Then we move the current to the next link, or to the next node. Current equals current.link. This section discusses how to insert an item in and delete an item from a linked list. Consider the following definition of a node. As before, for simplicity, we assume that the info type is int. We have a public class linked list node, public int info, and public linked list node link. We will use the following variable declaration in which head, p, q, and new node are reference variables of the linked list node type. Linked list node, head, p, q, and new node. Consider the linked list shown in this figure, figure 4-8. Suppose that P points to the node with info 65 and a new node with info 50 is to be created and inserted after P. The following statements create and store 50 in the info field of a new node. New node equals new linked list node. This creates the object new node with data or info 50. New node.info equals 50. This stores 50 in the object new node. The first statement, that is new node equals new linked list node, creates a node somewhere in memory and store the address of the newly created node in new node. The second statement, that is new node.info equals 50, stores 50 in the info field of the new node. The following statements insert the node in the linked list at the required place. New node.link equals p.link, p.link equals new node. After the first statement, that is new node.link equals p.link executes, the resulting list is as shown in figure 4-9. We can see that the new node's link is now pointing to the link pointed to by P. After the second statement, that is p.link equals new node, the resulting list is as shown in the second figure. The arrow now of p.link points to the new node. Note that the sequence of statements to insert the node is very important because to insert new node in the list, we used only one reference variable p to adjust the links of the node of the linked list. If we reverse the sequence of the statements, we do not get the desired result. For example, suppose that we execute the statements in the following order. p.link equals new node.link equals p.link. The figure shows the resulting list after the statements execute. It is clear that new node points back to itself and the remainder of the list is lost. Using two reference variables, we can simplify the insertion code somewhat. Suppose Q points to the node with info 34 as shown in this figure. The following statements insert new node between P and Q. New node.link equals Q, P.link equals new node. The order in which these statements execute does not matter. To illustrate this, suppose that we execute the statements in the following order. P.link equals new node.link equals Q. After the statement P.link equals new node, the resulting list is shown in this figure. P.link equals new node. Notice that the P.link now points to the new node. The remaining list is not lost. After the statement new node.link equals Q, the list is shown in this figure. The link of new node now points to the node pointed to by Q.